if it's correct, it represents the biggest challenge to astronomy/cosmology and/or fundamental physics in the last 100 years. And it should lead to a complete revision of either or both. And I think we're back where we started, roughly speaking, back where cosmology started 100 years ago.
Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Nameland, who has been the greatest living philosopher before me. In this video I want to talk about a new paper. It has been published like 3 weeks ago, so it's very, very fresh at the time of the recording anyway. In my opinion, if this paper is correct, and that's a big if, so I emphasize, if it's not correct, if it has been retracted or falsified or whatever, then just disregard this video. But if it is correct, then it would absolutely demolish either modern cosmology / astrophysics, or possibly astronomy even, or modern fundamental physics, including things like quantum mechanics and even just, relativity maybe even. Alright, so the implications are big, and I'm really surprised to see that it only has like less than 3,000 views at the moment. And it was published in Nature, actually. I mean, one of the journals from the family of journals of Nature, but still, I mean, it's a pretty serious journal anyway. So it's very surprising to me because, again, according to my interpretation, at the very least, this paper might represent the biggest discovery of the last 100 years, possibly, since 1920s, I mean, which again has implications to either cosmology or fundamental physics, including things like quantum mechanics or relativity, or both actually. Alright, so that's why I wanted to make this video, so let's roll.
Alright, so this is the paper I wanted to talk about. It's very fresh, you can see 29th of August of 2025, and I'm recording this on 18th of September. This would appear on YouTube quite a bit later, a couple of weeks later in fact. So what is the paper talking about? It's talking about the fact, or at least the observations, that the redshift distribution in a large sample of 1.3 million, I repeat million, quasars shows a significant dipole anisotropy. I'll try to illustrate this in a minute for you, so in case you don't understand some of these words. But the other thing we need to note that this anisotropy is in the direction of the galactic center, okay? So this is pretty much everything we need to know from this paper. If you want to read it, I'll link actually everything I will show you in the description, so you can read it. It's free to read, so very good, right? Yeah, so a significant dipole anisotropy, what does it mean? So according to cosmological principle, right, the universe should be uniform and isotropic. What does that mean? Like, for example, if we are here, the observer is here, okay, and we look at objects, in particular, in this case, this would be quasars, denoted by these green dots over here, and this imaginary circle is just here to illustrate that they are located at the same distance from us. I mean, the same distance, the same radius, right? So yeah, according to the cosmological principle, the current cosmology, they should run away from us, right, in the expanding universe, or at the very least, we're measuring the redshifts from them, and if they are at the same distance, the redshifts should be the same, indicated by these purple lines. I mean, it's more like the velocity is indicated by the purple lines, but the velocity is inferred from the redshifts anyway, so it doesn't matter. The redshifts should be the same, okay? In every direction, if the distances are the same. However, what the paper says is that in reality what we observe is that there is a certain like special direction, let's put it this way. By the way, I only painted 4 just to save time, okay? I could have painted like 100 of them. So there is a special direction such that in this direction there is, if you wish, not enough redshift, okay? And in the opposite direction, there is too much redshift. While at the right angles, the redshifts are kind of okay, they are as expected. I hope you can understand this. So from this, we can infer that, like, virtually, it looks like we are going in this direction. So we are, roughly speaking, catching up with this upper quasar. Okay, so with respect to us, it's moving slower than the others. And conversely, with respect to this quasar, like, we're moving faster from it just because of our, again, inferred velocity. Do you get the idea? So this is what the paper reports, basically, that the cosmological principle kind of wants us to observe this, but in fact we observe this, right? So in some direction, the quasars are biased in the sense of redshift. They have smaller redshift than expected, and in the exactly the opposite direction, there is more redshift than expected, whereas at the right angles, the redshifts are kind of normal, right? So, and this direction happens to coincide with the direction to the galactic center. So if the sun is here, then the galactic center would be there, which is extremely strange, right? So let's talk about this for a moment. By the way, the velocity that we infer from this, in fact, I'll show it to you in the paper itself, is, 1700 kilometers per second. And that's a huge velocity, okay? Let's talk about this for a minute. So the observation of these faraway quasars, like, I don't know how far, like hundreds of millions of light years away at the very least, okay, infer that we are moving, like the redshifts are biased in such a way that the quasars, roughly speaking, around the galactic center, I mean, it's all statistical, right? We're looking at 1.3 million, so we're looking at the whole sky. But the whole sky is biased in such a way as if virtually we were moving towards the galactic center with this sort of velocity. Hopefully you can understand this. By the way, a small comment here is that I liked a lot about this paper is that basically, like, first of all, the author acknowledges that there could be many concerns, like many biases. In fact, many biases in the set of data, etc., etc., etc. So I emphasize that it's not guaranteed that this result is correct, okay? However, I think the author did a really good job, and I want to sort of, acknowledge this, that this is really not a paper about physics even. It's a paper about data analysis. So it's as close to raw data as possible, if you wish, okay? Even the title suggests, right? Inferred velocity, motion, right? He doesn't say that it is motion. We're just inferring the motion from the bias in redshift distributions, right? So this is pretty cool. So I have to emphasize that it's not guaranteed that this paper is actually correct in even the observation of this redshift bias. But if it is correct, then it is huge. The implications are gigantic. Now I just did this. So what are the implications? How can we explain what is observed? Like this seeming bias, because again, the quasars should be independent of our galaxy. They're so far away, right? The galaxy cannot influence them in any possible way. Neither can the sun, for example. Like our velocity with respect to the sun is only 30 kilometers per second, right? So it can't be our velocity with respect to the sun. Neither can it be our velocity with respect to the galaxy. I mean, the sun's velocity with respect to the galaxy, because our orbital velocity is only 260, right? So if it was the sun moving towards the galactic center with a velocity of 1700, it would mean we're basically not even orbiting the galaxy. We're just straight up falling to the galactic center, right? So the galaxy wouldn't even exist in the first place. Okay, then it means it probably, you can explain this with the velocity of the galaxy itself, right? Or maybe like a whole galactic cluster. Well, then the question arises, why does this motion align with our line of sight, with our, I emphasize, with our line of sight to the galactic core? That would be a very strange coincidence, right? If the galaxy itself moved in such a way that, you know, the sun would lie at the same line as the galaxy and the direction of its motion and the sun. Like, it would be strange, right? And in fact, like, the author actually analyzes this case. Let me show you. It's not even my analysis 100%. Like the author also talks about this. let me see. Yeah. So happens to coincide, right? He says. So it should be a coincidence, basically. You can't explain this from cosmological principle otherwise. Or is it? I mean, it's a very strange coincidence, right? There are too many coincidences, maybe, at this point. So if it's not a coincidence after all, then it doesn't make any sense in the current understanding of physics, the current understanding of cosmology. And keep in mind, I have to underline this, that this is new data. Like, neither Big Bang cosmology nor any alternative cosmology, at least to my knowledge, is informed by this observation. So this is legit new data. Like, no one knew until this paper that there is such a thing, that if you look at very, very many quasars, you will see a dipole anisotropy in the redshifts of this sort, right? That the redshifts in one direction are too little, and then in the opposite too much, and then every other is okay. Okay? So, yeah. So what does it mean? By the way, one small note. There is also a sort of a large-scale anisotropy with respect to the cosmic microwave background. If you observe the temperature of the cosmic microwave background, you will have a dipolar anisotropy, but it's almost at the right angle to this. So it's in, roughly speaking, this sort of direction, or this, like, depending on how you orient the picture with respect to the galaxy, or maybe towards us or away from us in this picture. But it's almost at the right angle, So it cannot be connected to this cosmic microwave background thing, which is contained in Big Bang cosmology, for example. And again, many other anisotropies, such as active galactic nuclei characteristics, for example, they are connected to the CMB dipole. So this effect that we observe has nothing to do with it, right? So this is something legitimately new, and this is something that no one has known for now. What does it mean? We'll have to rewrite cosmology, probably. Or maybe something else. And again, the velocity inferred from the CMB, cosmic microwave background dipole, is 370 kilometers per second. So it's what? 5 times smaller, more than 5 times actually, right? So this effect is more important. This effect that we are talking about here. So once again, I have to underline, I have to conclude probably even, that if correct, I emphasize these words once again. This could be the biggest challenge to astronomy and cosmology and or fundamental physics in the last 100 years. So it should lead to a complete revision of either or both. Either the astronomy and cosmology or fundamental physics, or maybe both. So the situation right now, I think, with this discovery, if it is legit, I keep repeating, okay? If it isn't, you can just forget everything I said in this video. But if it isn't, if it is legit, then we are in the same situation where people have been in 1920s. That is exactly 100 years ago. That's why I give this figure of 100 years. When we've had this so-called great debate in cosmology, which basically started the modern cosmology to begin with. So what is the great debate? It's the, the debate on the nebulae, I don't know how you pronounce it in English. Basically, the question was, are what we currently understand as galaxies really different galaxies, or are they just smaller objects within our galaxy? So is our galaxy everything there is, or are there other galaxies? So basically, again, what is the scale of the universe? And obviously, if you don't even understand that there are other galaxies, you will arrive at a completely different cosmology with respect to the one that we're currently having. Okay? So it is this level of inquiry we're in, if this is correct. Okay? That's why I'm saying that this is probably the biggest discovery in astronomy/cosmology in the last 100 years. And also remember that around that time, quantum mechanics have been developed. So in case we'll have to rewrite fundamental physics, perhaps we'll have to rewrite something like this. So my sort of prediction of what's going to happen with this discovery, well, there is of course a safe case that it would be just falsified. So maybe again it's erroneous in some way. It's like there was bias in computation or whatever, or observational sort of biases. So it could be falsified. And again, if it is, then just forget about this video. Okay, but the worst case is that it is actually correct, but it would be completely ignored. Like, look, I know this paper is only 3 weeks old, roughly speaking, but there's only like 2,000 reads, right? 3 almost. And like at this point, this level of discovery should have 3 million reads at the very least, okay? That's what I would say. So it could be the case that this is a genuine discovery, but we are so far gone, let's put it this way, that would be just simply ignored, okay? This is a legit possibility. However, there is a third possibility. If it is true, and it would be even acknowledged, they could invent some stupid explanation in quotation marks. They might even call it the dark redshift or something, you know? I mean, speaking about dark matter, dark energy, etc. So it would be yet another useless patch to hide the holes in our understanding of the world. I mean, if we come up with crap like this, okay, in order to save our current cosmology, our current fundamental physics, which is basically the where the dark matter and the dark energy comes from in the first place, right? So maybe this thing will be motivated by the same thinking, or maybe, I don't know, best case scenario, like maybe third time's the charm. Maybe there would be enough dark stuff and people would realize that, you know, the problems are there and we can no longer ignore them, okay? Right, so this is the factual side of things. I'm pretty much done with the factual side of things. However, in case you're interested, I would like to propose you my own interpretation of what's going on based on my recent delving into Kozyriev's causal mechanics, right? Kozyriev's theory of time, etc. So it's just that I saw this paper roughly when I was making the video about Kozyriev, so it immediately struck me that the measured peculiar velocity, the one that we infer, I underline this word, right? From this dipolar anisotropy in quasar redshifts, the velocity that we infer from it, nevertheless, is really close to the velocity of causality. And by the way, in case you don't know what I'm talking about this. So I'm gonna link this video in the description where I describe Kozyrev's theory and where this velocity comes from, what does it mean, etc., etc. So this velocity is not far from Kozyrev's velocity of causality, which is the speed of light times alpha, which is roughly 2200 kilometers per second, right? So given that this is a statistical effect, this bias in redshifts, it could be the case that the actual velocity is actually this. I mean, it's pretty close, right? The order of magnitude is really close. The same, I should have said, the order of magnitude. Yeah, so how can you explain this? Well, long story short, I don't know how to explain this, but I have an idea of how to approach an explanation. It's like the Pirates of Caribbean, right? Do you have a key? No, I have a drawing of a key. So remember that Kozyriev was really concerned with the way stars produce energy. And since stars are basically the biggest contributor to entropy, right? Stars are the biggest source of irreversible processes. So where are most stars located? Well, it's easy to see that it's the galactic cores, right? Really interesting suggestions, but anyway, it's the galactic core, right? Look at how bright. I mean, obviously it's not our galaxy, but for obvious reasons, we cannot look at our galaxy like this because we are in it, right? But anyway, the galactic core, look how bright it is, right? It's the biggest source of entropy near to us. Like, let's say the sun is somewhere here. So this is the biggest machine of entropy / energy / time nearby. So it would influence the causality, again, according to the theory of causative. So could it be that this influence, and I have to emphasize, we have no idea how it works exactly, but anyway, could it be that this influence of the galactic core biases our temporal perception, i.e. the causality itself, and kind of mimics the additional redshift away from this direction? So I don't really want to say these words, but I'm kind of forced to, because we have no other terminology yet. So this influence kind of warps the very fabric of time, if you wish, in a way. So that the quasars, the light from which arrives from there, or from the opposite direction, their tempo, the frequency, becomes affected. Because roughly speaking, time is anisotropic when we're moving there or there with respect to there or there, which is kind of isotropic. Hopefully you get the idea. Again, I have to apologize. I'm not trying to sell you some quantum divine magic crystals, here. I'm just dealing with the fact that we have no terminology for these kinds of effects yet. But this is my idea, that some sort of influence related to time itself, or causality, or entropy, if you wish, from the galactic core, since it's the biggest nearby source of such influences to us, this leads to the anisotropy of every other effect, in particular the bias and redshifts of faraway quasars in this specific direction, towards this source of, roughly speaking, entropy / time / causality, I don't know, like something like this. This is my idea. So what can we conclude from this hypothesis? It would mean that actually cosmological principle is okay. So you can assume that the universe is so this is basically a virtual effect, right? It's a virtual effect. I have to remove all of this, sorry. It's a virtual effect caused by the presence of this machine of entropy in this direction, right? So it kind of distorts the causality itself in this direction. This is kind of my idea, right? But how can this work exactly? I don't know. Once again, watch my video where I kind of give this quote from Kozyrev, who says that in order to understand the details, we need to build causal electrodynamics first, and it doesn't exist, right? So that's the problem. However, one peculiar evidence, pun intended, by the way, we're talking about the peculiar velocities to begin with, right? Peculiar motion. Anyway, one peculiar piece of evidence in favor of this interpretation, this is my interpretation on the rails of Kozyrev, okay? Because obviously Kozyrev did not know anything about this. Neither, again, this paper is like three weeks old, so you're getting the freshest news here, freshest hypotheses, right? Okay, anyway, there are a couple of papers which may support my hypothesis. In particular, that basically the hypothesis is that this is a virtual effect caused by these Kozyrev-like temporal influences from the galactic core itself, okay? So this is one paper. It's almost exactly a year old, by Mr. Shamir. So it says that the mean redshift of galaxies that rotate in the same direction relative to the Milky Way is higher than the mean redshift of galaxies that rotate in the opposite direction. Why is that the case? Well, it couldn't be the case, again, according to cosmological principle, right? However, if Kozyrev is right, then the mutual rotation of cause around the effect would lead to, again, some, roughly speaking, don't quote me literally, temporal perturbations, right? There would be observed some differences in these additional causal forces. So if the galaxy rotates the same as the Milky Way, we'll get one, roughly speaking, tempo of causality between us. So thus we'll observe certain degree of redshift. But if it rotates in the opposite direction, our relative rotation will be twice as fast, right? Whereas if we rotate in the same direction, it's 0, right? So with this, you get a different redshift. I hope you can see the idea. So, and also remember that, by the way, the second paper by the same author, it's actually from February this year, says that the number of galaxies that rotate in the opposite direction relative to the Milky Way is actually 50% higher than the number of galaxies that rotate in the same direction relative to the Milky Way. Interesting, right? So it looks like there is a preferential direction of rotation of galaxies in the universe, at least seemingly. So how can you explain that according to the cosmological principle where everything should be uniform everywhere, right? Well, in causative theory, the causal forces might introduce angular momentum, right? And again, the stars are the engines of this entropy, causality, right? So they are the sources of causal forces in some way. Again, very vague, very sort of out there kind of terminology for now, but we don't have any other yet, okay? Hence, these causal forces might introduce asymmetry in rotational direction of galaxies, right? So that's why we would observe something like this. Keep in mind, the universe as a whole might not have any preferential direction of rotation. The universe itself as a whole might not rotate anywhere, but it's just these clumps of entropy, such as galaxies, or rather entropy machines, aka stars, clumps of entropy machines, such as galaxies, would be biased in terms of their rotational direction, okay? Because, again, we have a bias of time, temporal direction itself. So maybe this bias in galactic rotation direction is caused by the bias of time, because time is asymmetric according to causative, right? It's anisotropic. Time is a pseudo-scalar, it's not a scalar. So time going forward and backward are different fundamentally. And thus maybe if time is going forward as it is, I mean by definition for us, then the galaxies would rotate as they do preferentially. And if you reverse the time, then the preferential direction would be mirror imaged, right? So perhaps this effect of bias in galactic rotation in a certain direction is simply a consequence or a corollary or an inference of the bias in that the time is going forward and not backward, right? That's the idea. But again, how exactly can this work? I have no idea. I'm just repeating the very same thing. As George Lucas said, it should rhyme, okay? Like, we need causal electrodynamics. I have no clue what's going on. But this is, I think this causative theory is the only theory I can see right now that can provide at the very least a hope of explaining this. Not only this, but also this. These two papers I've shown to you. Again, I'm gonna link all of them in the description to this video. Well, let me once again repeat that this paper that we started from, if it's correct, it represents the biggest challenge to astronomy/cosmology and/or fundamental physics in the last 100 years. And it should lead to a complete revision of either or both. And I think we're back where we started, roughly speaking, back where cosmology started 100 years ago. And maybe it's enough, right? Maybe it's enough of dark crap. Maybe we have to acknowledge that something is wrong at the very basics, perhaps at the very basics of our understanding of such simple, in quotation mark, things as time. And again, who's working with time? This guy, right? Watch my video about him in case you want to know more details.
Thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.